Welcome back to CST432. Today we'll look at Divide and Conquer Part 2. Some of the key concepts in this lecture is, first of all, what are some of the basic flow control statements for decision making? Secondly, how do we make use of the Behavior-Based Robotics Framework in programming a robot? And finally, implementation of this various concepts into the object grasping robot called Grasper. What is decision making? Decision making involves taking different actions based on inputs that have been received by the robot. Now, this chooses among multiple but finite options. And this typically we use such things as conditional statements like if, then, else, or else, switch, and case statements. We first look at how we can implement if, then, else statements. On the left, we have the pseudocode, which is basically C code for implementing if, then, and else. Here we have a if operand 1 condition operand 2, which is basically an expression that satisfies a certain logic output. If that expression is true, then we will implement the if clause. Else, if the expression is false, we will execute the else clauses. This can be translated to ARM assembly language in the panel on the right. The if portion, we will first perform the comparison statement between operand 1 and operand 2, and based on the outcome of the comparison, we will have a conditional branch using the condition specified by the expression previously, so that if it is true, then we will jump to the label then. At which point we will execute the instructions related to the if clauses. If it is not true, it will fall through to the label else, at which point we will have the else clauses executed. And finally, there is a branch statement that is unconditional, meaning that you will skip over the rest of the then clauses to the NF statement label. Now in C language, there is something called a ternary clause that shortcuts this into a single statement. In this case, we have an output value that we want to assign to a variable called result. So we write it in such a way: result equal expression operand 1 condition operand 2, and then followed by a question mark, and when that is true, that is the if value that will be assigned. If it's not true, we will have the else value assigned to the result variable. This is implemented in ARM assembly language by doing the following. We have the compare instruction as usual between operand and operand 1 and operand 2. Then we use the conditional execution instruction in ARM to perform the movement or copy of the if value into the result if the condition is true. If the condition is false, we will use the not condition or the inverse of the given condition and do a conditional execution of the move instruction for the not condition, where the else value is copied into the result instead. It should be noted that the ternary clause evaluation using conditional execution is only available in the ARM state. Now, the other thing about the ternary clause evaluation is that it avoids pipeline flushing. As we know, if you flush the pipeline, it will store the execution of the program and cause the delay in the execution of the next instruction. So by using this approach, we can have constant execution time for expressions. Whether the if or the else portion is executed, you still take 3 instructions to go through the sequence. Now, unfortunately, it is not suitable for nested expressions, so it's only useful when you have ternary execution if then else statements. Now we will look into the Grasper robot. First of all, we will use the behavior-based robotics principles for implementing the Grasper robot. What's the objective of Grasper? It is first of all to follow the line until you sense an object, which uses a touch sensor to detect it, and then grasp it using the claws. The claws will close around the object to hold it in place. Now, the first behavior that we need is called the follow line behavior, and it's similar to the line follower robot we looked at previously. The second behavior is called the open clause behavior, which will take place when when there is no object being grasped and the claws are closed. We want it to open so that we can close it around an object when we bump into it. Finally, the grasp object behavior will close the claws around the object when the object is sensed by the touch sensor. This is the behavior diagram for grasper. On the left, we have the sensors. We have the bumper bar and the touch sensor used by the education set-based tripod that we have looked into previously. We have a light sensor for following the lines on the ground. And finally, we have a virtual sensor, because this is actually part of the motor device, which is the claw position sensor to allow us to determine the rotation of the motor for controlling the claws. These sensor values will be input into the behaviors in parallel, and each of the behaviors given here, grasp object, open claws, follow line, and idle, are prioritized with the grasp object behavior having the highest priority and idle having the lowest priority. All these behaviors are controlled by the arbiter to see which is the activated behavior, which will then program the motors with the appropriate output values. The arbiter also will provide some feedback to the behaviors, meaning the claw movement, whether it is closing or opening, as well as the robot state, which is used by the line follower to determine whether it is currently following a line or not following a line. The table shown here are the controller outputs for the various behaviors. For the grasp object behavior, the claw controller will close the claws, and the motor controller will stop movement. In the case of the open claws behavior, the claw controller is to open the claws as well as to stop movement of the wheels by the motor controller. For the follow line behavior, the claw controller is inhibited, meaning that it doesn't care about the position or the status of the claws, whereas the motor controller will be implementing the line following algorithm. Finally, if none of the behaviors are active, the idle behavior will be triggered. It's the lowest priority, where it inhibits the claw controller movements, but it will stop the movement of the robot in case that there is nothing to do. Now, these behaviors are arranged in priority order from the highest priority at the top row to the lowest priority in the bottom row. In this table, we see the behavior activation triggers for the various behaviors. For example, for the grasp object behavior, when the touch is active, meaning there's an object being sensed by the touch sensor, and the claws are open, the grasp object behavior will be activated. On the other hand, if touch is inactive and the claws were closed, open claws behavior will be activated. Now, follow line will be activated when the touch is inactive, but it does not care about the claw position, whether it's open or closed. Now, so follow line will only be triggered if open claws is not triggered, because follow line has a lower priority than open claws. And lastly, idle will be triggered if none other behavior is active. The arbiter used in grasper follows the fixed priority arbitration scheme. In this case, as mentioned, the higher priority active behavior always overrides a lower priority behavior, and only one behavior may be active at any given time. So by doing so, we can implement it in a low resource microcontroller such as that found in the next robot, because it doesn't require high number of resources for storing the variables associated with each behavior, as well as the CPU computation time for evaluating each behavior in turn. We will first look at how we can implement the arbiter using what is called preemptive multitasking. In such a system, a preemptive multitasking program will operate more than multiple behaviors in parallel. And the behaviors stated here, such as grasp object and open claws, will trigger if will be activated when the trigger conditions are met. And when the trigger conditions are met, they will perform a certain output action, as well as suppress any lower priority behaviors that may have been triggered as well. As you can see here, the follow line behavior is a bit more complex. It is triggered by touch being inactive, meaning that there's no object being touched. However, it would then perform different actions depending on the light input level. If it is within a range given for the black line, then it will go straight. If it is between the range given for an edge, then it will activate a slow counterclockwise rotation in order to reacquire the line itself. Otherwise, if we cannot detect an edge, it is within the lines, the value is given for white, which is outside of any line, then it will rotate a fast clockwise rotation in order to attempt to return to the line itself. We also add an unknown state where the motors are inhibited if we cannot recognize the color of the line on the floor. In contrast to a preemptive multitasker, a cooperative multitasker only allows a behavior to run under the control of the behavior itself, meaning that if the behavior is not relevant, it must then yield control of the microprocessor to the other behaviors for evaluation. In such a case, we will then evaluate the behaviors from the highest priority to the lowest priority order, because as soon as we encounter a high priority behavior that's activated, then the rest of the behaviors do not need to be evaluated. Now, in many real-time operating systems or real-time systems, we actually prefer cooperative multitasking. This is because we can achieve more deterministic timing for event handling, because the CPU is only yield to other processes when the current process is ready to do so. This allows us to know and time the amount of instructions or number of instructions needed to complete an action before we allow the CPU to do other tasks. Secondly, it is more suited to resource constrained systems, because preemptive multitasking scheduler will need to have to keep track of each process in a process data state entry in order to allow us to switch between them. Whereas in the cooperative multitasking arbiter, as long as the process or routine is not ready to yield to another process, you do not need to keep track of the variables in specific memory locations. Finally, we allow us by implementing a cooperative multitasking arbiter, we will need to require to implement a staggered processing approach, because we do not want to hold up the processing of a given behavior indefinitely and starve the processing of other behaviors. Now we look at how we can implement the Grasper controller. The main loop will iterate through various modules to implement the staggered processing approach. So if a behavior is triggered, it will indicate to the, for example, the claw to start opening or start closing. So this triggering of the claws to start opening will cause a value for the actuator to be programmed into the controller. And the actuation of motor is actually done in a different module than the behaviors of the arbiter itself to separate the two processes. This allows us to focus on evaluating behavior outputs and only program them to the actuator when the winning behavior is determined. So each module or routine in this cooperative multitasking environment must maintain its own state variables in order to allow us to start a behavior such as opening a claw and continue it over many iterations of the main program loop. So what happens is that processing takes place in chunks, small bits at a time, over multiple main program loop iterations. Here we look at the NxOS-Armdebug Robotic Framework, or NARF. The flowchart here indicates what happens in the program for the robot from the start to the end. At the top, we see the start bubble, which indicates that the program is initializing the various things such as the display and other variables. Then it will go into initialization of the robot, including preparing the sensors and the motors and so on. Next, we will start the main loop. The main loop is controlled by a evaluation, whether to continue the main loop or exit it. If it is to continue the main loop, then we will go through the following sequence. First, we will perform sensor readings to retrieve all the input values from the various sensors. Then we will execute the arbiter to evaluate the behaviors to determine which is the highest priority behavior that is active. Next, the highest priority active behavior will generate outputs that will be passed to the controller for it to program the actuators with the correct values. After the controller has programmed all the values to the actuators, such as the left and right motor and the claw motors, It will then go to a sleep state where we may delay the execution of the next program loop for a given amount of time. The reason why we have a sleep state is twofold. First of all, it allows us to control the period or the frequency at which we perform actions in the robot into a more reliable and stable manner. Secondly, it may allow us also to save power if the robot can be put into a low power state. So how do we perform the staggered processing or chunk processing in the robot? In this flowchart, we look at how various input values are processed. First of all, we have the sensor reading values. For the claw, we will retrieve the current claw position as well as the touch sensor status, whether it's touch or not touch. These values are stored into variables which are then used by the open claw's behavior to evaluate whether there has been a change in the current claw position compared to the previous claw position. If there is a change, it means that the claw is still moving. Now, if the claw is open or closed, it is indicated by a variable that will allow us to shortcut the evaluation process. If the claw is closed, then we will want to trigger the open claw's behavior. If it's already open, then by definition, you do not need to do any claw opening. So claw movement will be based on the position, rather the activity of the open claw's behavior, whether it is opening or closing. Based on the state of the open claw's behavior variables, we will then set the claw motor speed and the brake status, whether to keep opening the claw or to break the claw and set to 0 speed and force the claws to lock in place using a brake being true. So these values will be passed to the motor controller, which will then compare the new values for the motor speed and the brake status against the existing values, and only program the motor if there is a change. If there's no change, you will eliminate the reprogramming of the claw motors to save on processing overheads. So now we look at the various modules that make up Grasper. First of all, there are the general algorithms such as the min-max algorithm used for determining the line type. Secondly, there's a system housekeeping routines which used for program initialization and shutdown. Third, there are common robot operations such as initialization of the sensors, the motors, as well as to shut down the robot or else to sleep if there is excess time available in the main loop iteration, as well as the actual program main loop, which will iterate through the various routines in turn. Next, the more important to us is the Behavior-Based Robotics Framework routines such as the Arbiter and Controller, which controls the execution of the various behaviors and programming of the actuators such as the motors. Finally, the worker routines, which are the robot-specific routines such as actuator primitives, whether to turn on the motor, to go left, go right, to open the claws and close the claws, and so on for actuators. The sensor primitives to read from the various sensors and return the values in the appropriate variables. Sensor input routines to determine, for example, for the line follower, what is the line type. State display routines for us to debug the state of the robot by displaying a string onto the LCD screen, as well as specific behavior routines to implement the various behaviors in the Grasper robot. Okay, now we shall see the Grasper robot in action. First, we have the robot on top of the track that we see here, and the object that we want to capture. Now in this case, the object has to be of a certain dimensions. It has to be small enough to fit inside the Grasper claws, and heavy enough so that when we bump into it with the bumper, that it will not tilt or move. In this case, we have used a small bottle here with weights put inside to weigh it down so that it will not move. In addition, I have added some duct tape to increase the friction of the item so that it will stay on the track. Now you may need to find suitable items that will fit this requirement. The important thing to note is that the height should not be so much that it exceeds the bumper location here and it obstructs the ultrasonic sensor, which we will use in another later example. So now we shall see the Grasper in action. First we place it on the track. And we notice that once we start moving, start up the program for Grasper, it will go through certain actions. The first action is to open the claws, because currently the claws are closed. And after the claws are open, it will trigger the next lower priority behavior, which is to follow the line until it hits the object, at which point the highest priority behavior, grass object, will be active. I hope you enjoy seeing Grasper in action. If you want more information regarding the robotics framework and so on, you can refer to the following references, especially Brooks, Jones, and Arkins. The source code for Grasper can be retrieved from GitHub at the following locations. See you next time.